In problem 67, chapter 6, we have this beam which is connected to the roof with these two cables at A and B. Everything is at rest, and suddenly this cable is gonna break. And the question is, what's gonna be the tension in this cable immediately after breaking this one? What's going to be the angular acceleration of the beam? So we need to find alpha of this and also the tension in this cable immediately after this cable breaks. So if I want to draw the free body diagram, after that break happens, we are going to have tension in this cable, and also we are going to have gravitational force, mg. And these are the only forces that we have. Now, think about Newton equations. Based on Newton equations, some of the forces in any direction is going to be mass times acceleration, right? But we have no idea about the acceleration of the centroid, acceleration of g. Let's call this point g. So acceleration of g is unknown. We are going to have two unknowns for this one. Alpha is unknown, tension of the cable is unknown, and also this cable is going to rotate too. Alpha of it is going to be another unknown. So we have so many unknowns. I would definitely suggest to think about this problem for half an hour. This is a tricky problem. You can solve it in using different methods, and probably we can find the correct solution. But I'm going to teach you a tricky method. So if you did that and thought about this problem carefully, see the rest of the video. We don't know what is the acceleration of g, but I can find it using acceleration of A and using alpha of the beam. Let's say alpha of the beam is in clockwise direction. And if you look at point A, which is connected to the beam, A is rotating about this fixed point. So it's going to move on a circle. It's going to have a circular path. So acceleration of point A is going to have two components, normal and tangential. The normal component is 0 because acceleration in the normal direction is equal to velocity squared divided by r. But there is no velocity at this moment. We are talking about immediately after breaking this cable. So there is no velocity at this moment. So acceleration in this direction is going to be 0, and all the acceleration of A is going to be length of the cable times alpha of it. And the direction of acceleration of A is going to be perpendicular to that cable. So this is acceleration of A. And acceleration of G is equal to acceleration of A plus acceleration of g with respect to A based on relative acceleration equation. Acceleration of g is going to be equal to acceleration of A plus acceleration of g with respect to A, which has two components, alpha cross r and omega cross r. By omega, I mean omega of the beam. But there is no omega. So the only acceleration of g with respect to A, the only component of it, is going to be alpha cross r, or half a L times alpha of the beam, which is going to be in this direction. So it's going to be simply half a L times alpha of the beam downward, right? Alpha cross r. If you use right hand rule, you're going to see it is downward. So if I use, for example, xy coordinate, then acceleration of g is going to be acceleration of A minus L over 2 times alpha of the beam in j direction. So this is going to be the acceleration of the center of the beam. Now, instead of using Newton equations, I'm going to use D'Alembert method. If you remember, we talked about this D'Alembert method, which is quite useful in some complicated problems like this one. To use D'Alembert method, we need to assume there is a force at the center with the magnitude of mass times acceleration of it, actually mass times negative acceleration of the centroid. So if I wanna show those forces, I need to multiply mass to the inverse of to the negative AG and add it to my system. So if I do that, then I need to multiply mass to negative A. So when A is in this direction, that the force which I'm going to add here to turn this dynamic problem to a static problem, the Lambert method, I need to add mass times acceleration of A and also mass times negative L over 2 alpha in J direction, which means I need to add a force in this direction with the magnitude of mL over 2 times alpha. Based on D'Alembert method, oh, actually one more thing. We need to add a moment to the center with the magnitude of Ig times negative alpha. So if alpha is in this direction, I'm gonna assume we have a moment at this point with the magnitude of Ig times alpha. Based on D'Alembert method, if you add this force and torque, then your system is gonna be, your problem is gonna turn to a static problem. Now I can say sum of the forces is gonna be equal to 0 in any direction. Sum of the moments about any point is equal to 0, right? Which is quite helpful. For example, I can say sum of the moments about this point is equal to 0, sum of the moments about G is equal to 0, or any other point. And also the best point you can use here to take the moment is this point. Why? Because I don't really care about acceleration of A. I don't want to get rid of it. The only thing I want to find is alpha and also TA. If I take the moment about this point, let's call it C, then TA and MAA, they're gonna cancel out. They're not gonna make any moment about this point. The only forces I'm gonna have are gonna be mg and also this force, and also I'm gonna have this moment too. Sum of all of those moments, moment of the forces plus this moment about point C, is equal to 0. So if I use that, I can find alpha in one line. Sum of the moments about point C is equal to 0 because we have a static problem here. No? So I'm gonna have, I have this moment, Ij alpha, moment is a free vector, moment of this moment about any point is the moment itself. Then moment of TA and this force about point C are 0, so I don't need to write them. Moment of mg is going to be mg times this distance. And this distance is equal to this length times cosine of 30 degree. This angle is 30 degree, right? If I multiply this length to the cosine of 30, it's going to be the distance between point C and mg. But what is this distance? This one is going to be half of L times cosine of 30. So this is half a L cosine of 30. I need to multiply to another cosine of 30. So it's going to be the distance from here to here is going to be 1/2 of L times cosine of 30 times cosine of 30, or cosine squared. So moment of mg is going to be mg times distance negative, and also moment of this one is going to be this force. Is going to be this force times this distance in the positive direction. So I'm going to have plus 1/2 of L times cosine squared of 30 times ml alpha divided by 2 minus mg. And I have nothing else. It's equal to 0. And what is Ig? Ig is going to be 1/12 mass times length squared, right? So if I replace Ig with 1/12 ml squared, if I replace it over there, the mass is going to cancel out. And also I'm going to have L in, I'm going to have it in terms of L, I mean acceleration. So if you simplify it, you're going to find alpha directly from this equation. which is going to be equal to 18 times G divided by 13 times L. So this complicated problem, we actually found alpha just in one line, which is quite impressive. And the other part of the question is, what is this TA? So after finding alpha, now to find TA, we can use another static equation. For example, I can say sum of the moments about G is equal to 0. So sum of the moments about G is equal to 0. Moment of this force, this force, this force, they're going to cancel out, right? You're not making about moment about G. We have this moment, which is Ig times alpha. So we need to write it down. And also we have TA. Moment of TA is going to be TA times half of L times sine of 60. And the direction of the moment is going to be clockwise, negative. So I'm going to have negative 1/2 of L times TA times sine of 60 is equal to 0. We know what is alpha here. We can put it here. And also we know what is Ig. If you put everything over there, T is going to be equal to, TA is going to be equal to 2 the square root of 3 divided by 13 times mg.